So we're already in pretty good shape with E2 chemistry, but I just wanted to make a condensed review sheet. So with an E2 reaction, we said that you have to have some sort of leaving group similar to with substitution reactions. You have to have some sort of strong base. And when you do this, you can end up with a variety of different products. Actually, let me add in one more carbon on there. You can end up with a trans alkene. You could end up with a cis alkene. Both of these would be considered your Zaitsev or Hofmann products. Zaitsev, they'd be more substituted. And then last but not least, you could have your Hofmann product. So these are your Zaitsev. And we said that this is usually our major Zaitsev. And this would be our minor Zaitsev. And I'll just call it minor S or major S and minor Z. And then over here we've got our Hofmann. And with E2 reactions, it always requires a super duper strong base to occur. So let's make a note of that. E2 requires a strong base, similar to an SN2 where an SN2 requires a strong nucleophile. And we said that oftentimes good bases are things like sodium hydride, DBU, DBN. And these are all non-nucleophilic. That means that you're not going to observe any competition with substitution chemistry if they're not nucleophilic. However, there are some classes of nucleophiles or bases that are nucleophiles. These would be things like sodium hydride, or sodium hydroxide, sodium ethoxide, or really any sodium where this R group isn't super duper bulky. These are nucleophilic bases. Nucleophilic bases can do substitution chemistry, so we have to be careful when we use them to watch out for that. The second thing we said was Zaitsev is favored by small bases. And Hofmann is favored with large bases. What sort of base works well with Hofmann? Yeah, tert-butoxide, something that's got a lot of alkyl spinach hanging off of it. Last thing we said was elimination is favored at high temps. Just like we saw in lab, you typically want to crank the heat up in order to drive that elimination reaction. The beta proton must be anticoplanar. And when we're looking at the substrate, does it matter whether or not it's primary, secondary, or tertiary? The thing that we're working with? What do you guys think? Matters a little bit. However, it's actually the flip of SN2, right? We said SN2, the primary goes faster than secondary, and it doesn't even happen with tertiary. E2 rates actually favor more substituted substrates. So let's make a note of that substrate can be primary, secondary, or tertiary. And we know that more substituted substrates occur faster. Have faster E2 rates, and we said that that's due to hyperconjugation. Do we ever observe E2 with methyl groups? Something like methyl bromide. So let's say I've got CH3 with a bromine attached to it. Will this ever do E2? Why not? Yeah, no beta protons. So that's also a simple clue too. Is you can only ever have E2 with the primary, secondary, or tertiary, but you can have SN2 with the methyl carbon. All right, so let's switch gears and talk about E1. Good news is E1, I think, is pretty straightforward and simple, and then we'll go through some more challenging practice problems. And with E1, we already did some basic mechanisms. And we said with E1, it's similar to SN1, where you have a good leaving group. And what's the first step going to be? Yeah, leaving group falls off. That's going to leave us with a carbocation plus our leaving group. It's just hanging out over here. And then next step, we'll have a base. And we need to deprotonate beta protons. And in this case, the beta proton is off of the carbon adjacent to that carbocation. So it has to be one carbon away. So for example, we've got beta protons coming off of each of these methyl groups. And we can grab one, we can clamp down, and we end up forming an alkene plus our protonated base. It's a really straightforward reaction, and it follows a lot of the same rules as SN1 reactions. You have to be able to form a really stable carbocation. So let's make some notes. You must have a good leaving group. And you must form a relatively stable carbocation. Or rearrange into one. In this case, do you think we need to have a strong base? Probably not. Our carbocation is super duper unstable. We only need something to help push it over that edge, you know? If we have a strong base, what's the problem? Yeah, I could do E2. So strong bases always favor E2. Weak bases will not do E2 reactions. So in this case, you only need a weak base. Something with a lone pair will work. And like we said, a strong base favors E2, not E1. And we said that our beta proton is next to the carbocation. A lot of people get confused and they say, well, what if there's a rearrangement? That means that your beta position will actually move to the carbon containing protons next to your new carbocation center. So you have to account for that. The other nice thing with this is that your beta protons don't need to be anticoplanar. Thanks. Why do you guys think it doesn't need to be anticoplanar anymore? What's special about the carbocation? What do you guys think? Think about it. You've got this empty p orbital. Everything else is planar. It really doesn't matter where that beta position is going to be. It's not going to be influenced because the leaving group's already long gone. So in this case, you don't have to worry about stereochemistry as much. It makes these problems a lot easier. The other cool thing with this is that the reaction always favors the Zaitsev product. Let's do E1 always favors the Zaitsev product. There's one big problem with E1 though, and that's it follows all the same rules as SN1. So oftentimes when you do it, you observe a mixture of E1 and SN1 reactions. They're really common. The other last thing is if we do want to favor E1, there's a trick. And that was a trick we did in lab. We did an E1 reaction in lab, and we used what in order to favor it? Heat and acid, right? So if you've got heat, acid, and an alcohol, that usually will favor an E1 reaction. So we'll do heat plus strong acid plus alcohol equals an E1. The question is, what strong acid is typically favored? Normally you'll do sulfuric acid or phosphoric acid. Why don't we want to use something like HCl in this case? HCl is a strong acid. Yeah, the conjugate base is a good nucleophile, and it might actually do SN1 chemistry as well. The conjugate base for sulfuric acid and phosphoric acid are super duper bulky. They're not going to add in and do an SN1 product. So the conjugate base is too bulky for SN1. All right, let's take a look at some practice problems though. And I'll give you guys a little bit of time to work through these, and then we'll jump into more challenging ones. All right, for this practice problem, we're going to go with our tried and true E1 method. We're going to treat this with catalytic acid, and I'm just going to do H plus in brackets to avoid having to draw out all of sulfuric acid. And I'll write catalytic underneath, and then the delta symbol for heat. So let's go ahead and draw the full mechanism for this, and then try to anticipate what product or products we would get out. Once you're done, try to check with your neighbor to see if you guys agree. How about this? How about I work through it and you guys tutor me? All right? All right. I'm going to do this problem. I know the first step's going to be the leaving group falling off. No? Why not? Protonated first. All right? Good job. I'll keep you guys around as tutors. All right, so I protonated it. I'm remembering my positive charge. Okay, now I can kick off my leaving group. And if I do this, I've now got my carbocation. All right, I've got some beta protons. Should I pluck those off? Rearrange, right? So we've got a secondary carbocation, but we can do better. So let's go ahead and do a 1,2 hydride shift. And we've got water floating around still. So I'll do a hydride shift from here over to that secondary position. Why don't I do a methyl shift? Yeah, it wouldn't change anything, right? We go from secondary to secondary. You don't do rearrangements unless you form a more stable carbocation. Okay, so now I've got this tertiary carbocation. All right, I've got methyl groups here and here. Those blue protons are beta, right? They're next to that carbocation. Is that it? Yeah, we've got two more on this side. So looks like I've got a bunch of different beta protons. And I've got water too, right? So actually let me draw it down over here. The water that fell off can act as our weak base. Okay, so I'm going to just grab one of these. Does it matter which one? No, they don't have to be anticoplanar, so we don't have to worry about it. We'll clamp down. Okay, what about if I grab one of these and clamp down? It's the same product, so it doesn't matter. You can show it twice. You're just kind of wasting ink at that point, though. So I'm going to erase these. And then we'll try one more down here. And we'll say, all right, I'll grab one of these. We'll clamp down. All right, which one of these do you think is going to be our major product? The one on the right? Why is that? It's a Zaitsev product. So Zaitsev product is going to be favored. However, we will observe some Hofmann, and this will be our minor product. Pretty straightforward, right? Yep.
Will we not see any product from before the rearrangement?
That's up for debate. If you look in some textbooks, they'll say you might observe some E1 before rearrangement occurs. However, my general rule of thumb, if rearrangement can occur, it will occur, and draw your E1 products after rearrangement. Does that make sense? It'll make it a little bit easier just to conceptualize everything.
Was that true more specifically for E1? Because there was SN1 in the exam and there was multiple options if the chloride fell off?
So that's it. On the exam, we had a unique example with resonance. That would occur with E1 though, too.
Okay.
And that might show up on a pod, hint, hint. All right, you guys want to do some more practice? All right, let's try a different practice one. You guys want another easy one or a challenge one? Challenge? All right, let's do a challenge one. I like this one from the book. This one is 881, and it says, propose a mechanism. And the molecule is pretty large. And we've got catalytic acid. I'll just show that as H plus and heat. And our final product is now a different looking ring system where you've got double bonds in each cyclohexene. So let's try to propose a mechanism for this, and I want you guys to check with your neighbors, but this one's a little bit involved. All right, do you guys want to check in and go through it as a class? All right. So first step, we said anytime you've got strong acid is going to be a protonation step, right? Acid-base chemistry is going to be faster than any other reaction that can occur. Okay, so now we've turned that alcohol into a pretty decent leaving group, or actually a really good leaving group, because now it's a water molecule. Next step is going to be that leaving group popping off, right? So I'm just going to continue this going down. However, now we've got a secondary carbocation. What can we do to stabilize this secondary carbocation? Alkyl shift, right? All right. I'm going to do an alkyl shift from there to there. Does that work? No, it has to be a 1-2 shift, right? I'm seeing this a lot in practice problems where students try to do a 1-3 shift. Always remember that you can only do a 1-2 shift. That means we can only move one of these methyl groups over. Okay. Now if we do this, we're on our way. We formed a tertiary carbocation, which is better. Oh, I don't like this. There we go. So we're working in the right direction. However, can we do any other rearrangements to form a more stable carbocation? Hydride shift. Do you have a question? Hydride shift? All right, so we can move this hydride, right? We don't want to move the methyl group because that would form a secondary carbocation where this would form a tertiary. Okay? All right, so now we've got this methyl group here, and we've got our tertiary carbon right there. However, we're forming a tertiary carbocation from a tertiary carbocation. I told you guys that typically you don't want to rearrange to the same stability, but what's special about our second one? Resonance. Does anybody remember this type of carbocation where you have resonance? It's not benzylic. It's allylic. So anytime you've got a resonance stabilized carbocation where you've got a double bond next door, we call that an allylic system. Okay, so now what we can do is we can say, hey, we can draw the resonance structure. And if we do this, this pi bond can move up. Into this ring, which leaves this carbon as the tertiary carbon. And let's just put a box around it, or brackets, I should say, to clearly designate that these are resonance structures, not reactions. Okay, so now we're on our way. If we look at our final product, we need a double bond down in this position, so we've got to form a pi bond there. So let's show that. This is going to be a long arrow. And we've got water that was a leaving group. So in this reaction, we've got these two protons, and this water can come grab one of them, clamp down, and that will result in us getting our final product. Do you guys think there's any other products we could get? Yeah, definitely. If we look at the top one, the top resonance structure, if we pulled beta protons off of this position right here, we'd get the same product, right? That sigma bond could spin. However, if we look down here, there's another reaction that could occur. So I'm going to zoom back in on this. And we could say, you know what? This water could grab a beta proton off of this guy. And where's our beta proton? Or do we have more than one? Yeah, we've got two different types of beta protons, right? We've got beta protons here. Do you think that's going to be very likely that we end up plucking those off? Not as likely. We could definitely draw that as a product, but we also have a beta proton there. So now we could go ahead, grab this proton, clamp down. And we could end up forming this product. In fact, do you guys think this product will be major or minor?
Major.
Probably major, right? If we go back and we look at the other product, this alkene right here is tri-substituted and tetra-substituted, where down here we've got tetra-substituted and tetra-substituted. So I would say this would actually be the major product that we would get out of this reaction. This one's a little bit challenging. So this would be our major product because it's more substituted. However, the question was just asking for the mechanism going to that one product. So I'll try to give you guys some clear guidelines, especially when there's a whole bunch of different products. But in general, what I'm looking for you guys to show me is the more substituted potential product. Sound good? All right, remember, if you're in tomorrow's lab, bring your flowchart with you, and then make sure you bring your notebook too, because we're going to be doing a notebook check tomorrow in lab.